The physics behind tornado power. At its core, a tornado is a rotating column of air connecting a thunderstorm to the ground. But what makes it so powerful is the extreme pressure difference between its center and the surrounding air. Inside a strong tornado, pressure can drop by over 100 millibars, creating a suction effect so intense that it can make walls explode outward as the air rushes to equalize. Combine that with rotational speeds that can exceed 300 miles per hour, and you have an engine of destruction fueled by physics itself. The energy released by a single EF5 tornado can rival the explosive force of a small nuclear bomb. Wind speed, the heart of tornado strength. Tornado wind speeds vary drastically. Weak ones, rated EF0, may only have winds of 65 to 85 F, but the strongest, EF5 tornadoes, push beyond 200 miles per hour and in rare cases, approach 320 miles per hour. To put that into perspective, a Category 5 hurricane has sustained winds of around 157 miles per hour. Tornadoes can double that speed, but within a much smaller area, concentrating their energy into a narrow path of devastation, sometimes only a few hundred yards wide. When those winds hit buildings, trees, and cars, they create deadly projectiles. A 2x4 wooden plank can pierce through metal, and vehicles weighing over a ton can be thrown hundreds of feet. Pressure drop, the invisible destroyer. The drop in air pressure inside a tornado isn't something you can see, but it's one of the most destructive elements. When the pressure drops suddenly, structures can implode if the air inside doesn't have time to escape. During the 1974 Xenia, Ohio tornado, entire homes appeared to explode, not because of wind impact alone, but because of this pressure difference. It's a split-second effect that turns stable buildings into rubble. Rotational energy and angular momentum. Every tornado is a masterclass in angular momentum, the physics principle that keeps spinning objects spinning. As warm, moist air rises into a thunderstorm and begins to rotate, it tightens into a smaller column, just like an ice skater pulling in their arms to spin faster. This tightening effect causes the wind speed to increase dramatically. In the most extreme tornadoes, the rotation becomes so fast that the centrifugal forces balance the inward pressure, allowing the funnel to sustain itself for miles. That's why you'll sometimes see multi-vortex tornadoes, smaller funnels rotating within the main one. Each of those sub-vortices can have wind speeds even greater than the main funnel itself. The power of the updraft. Updrafts are what keep a tornado alive. In supercell thunderstorms, the type most likely to produce violent tornadoes, updrafts can reach speeds over 150 miles per hour, carrying debris, dirt, and even vehicles high into the air. This rising air feeds the tornado from below, continuously supplying it with energy and momentum. In powerful tornadoes, radar scans have shown debris being lifted over 30,000 feet, meaning items picked up from the ground can literally enter the upper atmosphere. Real-life examples of sheer force. The 1999 Bridge Creek Moor tornado in Oklahoma is still one of the most powerful ever recorded. Mobile Doppler radar measured wind speeds at 302 miles per hour, the highest ever observed on Earth. Houses were not just leveled, but completely removed from their foundations, leaving nothing but concrete slabs. Another shocking case was the Joplin, Missouri tornado in 2011. Classified as an EF5, it flattened over 7,000 homes, destroyed hospitals and schools, and killed 158 people. The damage pattern was so extreme that debris from Joplin was found over 70 miles away. These storms demonstrated to the world that despite modern construction, no man-made structure can withstand the full force of a tornado, the force on structures and objects. To understand tornado force, consider this. At a 200 miles per hour wind speed, the pressure exerted on a wall can exceed 250 pounds per square foot. That's like having a car pressing against every square meter of your home, all at once. That's why engineers study tornado-resistant design using anchors, reinforced concrete, and aerodynamic roofs. Still, even the strongest shelters can only withstand so much. When the most violent tornadoes strike, survival often comes down to luck and timing. The EF scale and what it really means. The enhanced Fujita (EF) scale rates tornadoes from EF0 to EF5 based on the damage they cause. But what many people don't realize is that the scale measures destruction, not direct wind speed. An EF3 tornado might have winds near 160 miles per hour, while an EF5 exceeds 200 miles per hour. But because not every area has structures to destroy, many of the world's strongest tornadoes could be underrated simply due to a lack of visible damage. The true force of nature, in some cases, goes unmeasured. Tornado size versus power. Bigger doesn't always mean stronger. Some massive tornadoes a mile wide might only reach EF2 intensity, while smaller, tighter ones can pack EF5 force. However, when size and intensity combine, the results are catastrophic. The 2013 El Reno tornado, also in Oklahoma, was nearly 2.6 miles wide, the largest ever recorded. Though it was classified as EF3, its scale alone made it impossible to escape. The storm's winds changed direction rapidly, confusing even experienced storm chasers. What happens inside the core? Inside the tornado's funnel is chaos, extreme turbulence, low pressure, and moisture condensation forming the visible vortex. The innermost region, just a few meters wide, is where the strongest winds occur. Air moves upward and inward simultaneously, creating a spiral that can grind buildings into dust. Scientists have tried for decades to measure what happens inside, but very few instruments survive. The data we have mostly comes from radar or debris analysis after the fact. Why tornado force is so difficult to predict. Despite all our technology, predicting the exact strength of a tornado before it forms is nearly impossible. Meteorologists can identify supercell conditions, wind shear, and instability. But once a tornado touches down, its intensity depends on small-scale factors we can't yet model. That's why some tornadoes suddenly strengthen or weaken without warning. The local wind flow, temperature changes, and ground friction all play roles in how much power is unleashed. Nature's most violent force. When you see a tornado tear through a town, you're witnessing the atmosphere release its energy in the most concentrated way possible. Tornadoes remind us how fragile human structures are compared to the power of nature. From pressure drops and rotational speeds to debris fields stretching miles wide, every tornado is a force beyond comprehension. A reminder that for all our progress, we're still at the mercy of Earth's weather when it decides to unleash its full power. The sound and shockwave of a tornado. People who've survived direct tornado hits often describe the sound as unlike anything else. A roaring freight train, a jet engine, or even an explosion that never ends. This noise isn't just wind, it's the result of air turbulence and debris impact on every surface in its path. Large tornadoes generate acoustic shockwaves that can travel for miles. In fact, some scientists use infrasound sensors, devices that pick up ultra-low frequency sound waves, to detect tornadoes before they're visible. That gives researchers one more way to study their immense power. Measuring the energy of a tornado, you might wonder, how much energy does a tornado actually produce? The answer is staggering. A large EF5 tornado can release as much energy as 10,000 tons of TNT, equivalent to several small atomic bombs. Most of this energy is in the form of wind kinetic energy, not heat or light, but sheer motion. The concentrated scale of that energy is what makes tornadoes so destructive. While hurricanes release more total energy, tornadoes unleash it over a much smaller area, making them far deadlier per square mile.